G'day guys, today we're going to start off with the first half of 10.3. So this exercise will go across two lessons. So it will be today and Monday's class for my class. A lot of it will involve some backwards scanning, which we did look at in the previous video, but we'll look at it a little bit again today to consolidate. In this part of the video, we'll also be looking at dummy activities, and the next lesson will be focusing pretty much solely on what's called crashing. All right, so a couple of things that we need to go over first. So we didn't cover this in the last video, is two rules when it comes to backwards scanning. All right, so when we have a graph or network and we're doing a critical path analysis, we must adhere to these two rules. Otherwise, it's not physically possible for us to do a proper backward scan and therefore a full critical path analysis. So first of all, rule number one, two vertices can be connected by a maximum of one edge, so no parallel edges or no multiple edges as we define them as in the first part of today's topic. And rule number two, an activity must be represented by exactly, that should say one edge. All right, so those two diagrams there, if they were to exist inside our graphs that we're doing a critical path analysis, they would violate the rules. Therefore, we wouldn't be able to do a proper backward scan and therefore the critical path analysis. So no A and B connecting to the same two vertices like so. So towards the end of this video, we're going to be talking about what's called dummy activities. That's how we can get around these two rules and still do our full proper critical path analysis. The formula on the bottom there, float, we did look at that last lesson, but just there again for your notes in a more wordy way, is the latest start time of the next activity minus the earliest start time of the current activity minus the current activity time. And we're going to do a pretty large example in this video, which we'll be practicing the float time. All right, so first of all, what we're going to do is we are going to do a full critical path analysis on this graph. And then on the next slide, we're going to convert that information into a table. So for the way your notes are set out, I would have draw this graph up. We're going to draw all the little houses on it and fill in all the information. And then when I do the table on the next slide, make sure you are writing the table underneath this so that all the information matches up. All right, so as we know by now, we have the little houses that involve a triangle and a rectangle. So for each of these vertices, we need to draw that little house. I'm sure yours will be much neater than mine. Some source materials that, if you do any further research on this, will show these houses not in this form, but they'll rather be like two squares or two rectangles side by side. So if you ever see that, don't stress, it's the exact same thing. That'll do. Cool, all right, so now we're going to go through and we're going to calculate our earliest starting times with our forward scan. So we're going to fill in the triangles or the top parts of each of these vertices. As we know, we always start off with a 0. All right, so as we move through here, activity A, which goes for a total of 2 minutes, or depending on the context of the question. Moving on, we have coming off A, we have B, which will give us a total of 5. Down the bottom, also coming off A, we have C, which has 5 for a total of 7. Next, in the middle, we have E and F coming in to create a vertex there. So we have two options. We got 2 and 2 for a total of 4, or 7 plus the 6, 13, which is much larger, so that'll go next. All right, so then coming off that, so we'll follow H. We've got two options, 5 and 7 for a total of 12, or 6 and 13 for a total of 19. Again, that's our larger number. Down the bottom, we have I and G coming into a vertex, so 13 and 3 for 16, or 7 and 8 for 15, so 16 is our larger number there. Coming off J and K, we have another vertex, so we have 19 and 2 making 21, or 16 and 4 making 20, so we'll go for 21. And after that, we have L for 1, so a total of 22. So that's our earliest completion time for the entire project, 22. All right, so now we need to perform our backwards scan. So when performing our backwards scan, as we know, what we do is we write in the smallest valued number. So as we did a forward scan, we were writing our largest. When doing a backwards, we write the smallest. So rewrite whatever number that you got for your earliest completion time in the rectangle below, or square. And as we go, we subtract values. So 22 take 1, 21. My next option is we'll follow path of J. So 21 take 2 is 19. If I followed K, 21 take 4 is 17. My next one, I have two options coming in. So from 17 along I is 3, so 14. Or 19 take 6 is 13. So again, as I said, we go through that and do the smallest value. So that one will be 13. Along the top there, so the D, which has a value of 7, we have 19 take 7, which is 12. So the numbers I'm subtracting from here are the latest starting times, the ones I'm writing in green. Down the bottom left there, so I've got a couple of options coming into that one, so F and G. I can go 17 take 8, which is 9, or 13 take 6, which is 7, so I'll go for the 7, the smaller value. Got a few options coming into that house with a total of 2 on its roof, so I've got the 12 take 3 is 9, 13 take 2 is 11, or 7 take 5, which is 2. I'm going to go for the smaller number. And finally, 2 take 2 is 0. So you should definitely finish on 0. If you haven't, we've done something a little bit wrong. So now I can identify the critical paths. So the critical path is where the number in the top and the bottom is the exact same, and I follow that route. That's my critical path. So in this case, if I follow along, be A down to C, because in that I've got 7 and 7. Following along up with F, up to H, J, and finally L. So that's my critical path for this network. So I'm going to write that out. It goes A, C, F, H, J, and L. All right, what we're going to do is we're going to translate that information into the table here. So the earliest starting times and the latest starting times, that's what the EST and the LST stands for here. And then the TX, that is just the values that were on those edges, so the times that they take. Now, A, its earliest starting time was 0. B's earliest starting time was 2. So these are just those values coming after, just occurring right before these events were occurring. So I'm going to go through and fill that out. For C, we had 2. For D, we had 5. E, we had 2. For F, we had 7, 7, 13 for both of these, 19, 16, and finally 21 just before L occurred. So these were taken from those little, from the triangles, sorry, of the little houses prior to these activities occurring. Sorry, I can't flick back to the graph. It doesn't let me do that in PowerPoint, which is a little bit annoying. And so then the latest starting times are just those numbers in the rectangles straight after the activity occurs. So after activity A occurs, we get the number 2. B in the rectangle, we get the number 12. 7, 19. So hopefully visually you can see where these numbers are coming from, looking at your graph and then the table. 13, 13, 17, 19, 17, 21, 21, and 22. Beautiful. Once you have got those values filled in, it's pretty easy to calculate the float time. All we're really doing is this value up to the top here, the latest starting time of Y, and then we're just subtracting the previous two values, the earliest starting time of X and the time of X. So the float time of activity A would be 2 minus 0 minus 2, which equals 0. So any activity that has a float time of 0, that is occurring on the critical path that we established in the previous slide. The float time of B, 12 take 2 take 3, is 7. So activity B can be delayed for 7 minutes without delaying the entire project. 7 take 2 take 5 equals 0. So therefore, activity C, yep, that was on the critical path that we established in the previous question. I'll do a couple more. Activity D, float time 19 take 5 take 7 equals, quick maths, 7. And I'll do one more. Activity E, 13 take 2 equals 9. All right, so go through and calculate the remaining float times. I won't do it on here for the sake of the video not going for too long. All right, the last thing I want to go through in this video is dummy activities. So this is an edge that we add to our network so that we don't violate those rules that we went through in the first slide. Typically, it's represented by a dotted line with an arrow going in the correct direction, and we just give it a time of 0 because the dummy activity doesn't take any time, but what it does is it allows us to do backwards scanning without violating the rules that we established. So let's have a go at drawing this graph here. Oops. All right, so what we have is two edges with 0 immediate predecessors, A and B. So that means we're starting with A and B. A has a time of 5, B has a time of 4. All right, C has both A and B as its immediate predecessors, so this is where our dummy activity comes in. If I did C as both A and B's immediate predecessors, it would just look something roughly like this. Now we can't have that. We can't have multiple edges connecting two vertices according to the first rule that we went through. So this is where we need to incorporate what's called a dummy activity. All right, so what we do is, because C is an immediate predecessor of both of these, we are going to write C just coming off either of them. It doesn't really matter which one. I'm just going to say it's coming off A. All right, so what I need to do is I need to connect this vertex that's coming off B up to the top there so that it can still be a predecessor for C. So what we do is we add in a dummy activity like this. We literally just draw a dotted line, give it the correct direction. When we draw it, we usually give it a little dash that notifies us it's a dummy and give it a weight of 0. And then finally we have D that comes off of B as another immediate predecessor. And so that would be our network. So when we have to do a dummy activity for it, that's how we draw it in. One more example, this one's a little bit bigger. So what we're going to do is we're going to draw a network based off the information here in the activity chart or table. So we have 3 activities. These ones don't have any weight on them, so I'm not going to bother drawing numbers. Got A, B, and C. All right, next I have D, which comes off of B. Now, just looking ahead, E comes off of A and D, so that means I'm going to connect D up to here so that activity E can come off of A and D. So this is, if you don't quite recognize that the first time around, that's why it's really important to join these as in pencil so that you can make those changes. All right, activity F comes off of B. Activity G comes off of C, and looking ahead, I is going to come off of F and G as well. It's also going to come off of E, but that's where we're going to have to put in our dummy activity in a moment. H comes off of E. And I comes off of E, F, and G. So I'm just going to put I there for now. All right, so this is where our issue is, that I comes off of E, F, and G. Now, currently with our structure, that doesn't really work, and if it did, we would be creating multiple edges. We would also have more edges for E than just one, so that's something that we can't have. So we need to put a dummy in here. We need to put it in the appropriate spot. So we need E up the top here to be a predecessor of I. So what we're going to do is going to add a dummy in, just like so. And give it a little dash as well. So what that does is now E, F, and G are immediate predecessors of I, while E is also a predecessor of H as well. All right, so that's it for today's video. Hopefully some of that made sense. As I've mentioned previously in class, just practice with all of these. All right, thanks guys.